Hello, good morning, afternoon, or evening, whenever you're joining us. This is the fourth and final video in the urinary system video series. In the first two videos, we talked about a lot of the anatomy. In the last video, which was video number 3, we talked all about urine formation. And in our fourth and final installment, we're going to be talking about regulation. So here we go. Okay, we ended in the last video going through the steps of urine formation. So just to bring you back to where we are, we talked about the nephrons in the kidney performing urine formation. The first step was glomerular filtration inside the glomerulus and the renal corpuscle. I think I have to sneeze again. Pardon me. Again, allergies don't stop even when I'm recording. So our first step was glomerular filtration inside of the glomerulus. Then we had tubular reabsorption and tubular secretion in the tubules. And our third and final step was water conservation, where additional water is reabsorbed in the collecting duct. Hopefully, through your study, you are going to, if not already, becoming experts at urine formation. But another important discussion, of course, is how we regulate this. And we're going to start with talking about glomerular filtration rate. If you're following along in the PowerPoint, this is just after the first step of glomerular filtration, the first step of urine formation. So remember, we talked about blood filtration at the glomerulus, where it filters by size. We talked about opposing forces, that the hydrostatic pressure is the pressure that the blood comes into the glomerulus with, and then the osmotic pressure are forces from the capsular space in to the glomerulus. God, I'm so sorry. And then we talked about the net filtration pressure. The net filtration pressure under normal circumstances, basically as long as we want the kidneys to be functioning normally, we have to have the hydrostatic pressure greater than the osmotic pressure. Remember that? And that's what keeps filtration happening in this direction. Because what's the alternative? If osmotic pressure was greater, that would mean that we'd have a backup in the plumbing. Instead of being able to filter from the glomerulus into the tubules, we'd be having a net pressure from here in. And that would pretty much completely disrupt our ability to filter at all. So we don't want that to happen. We want hydrostatic pressure to be greater, and that keeps fluid moving in this direction. Okay, good. Let's talk about glomerular filtration rate, GFR. I have to tell you a little story. When I applied for the job at Hudson Valley Community College, one of the things as part of the interview is that they assign you a topic and you have to give a lecture to the committee. And wouldn't you know, the topic they assigned me was glomerular filtration rate. I had to practice saying glomerular filtration rate even before I could figure out how to present it. And then presenting in front of, professors who are much older than me and have been around much longer in the field, it was a little intimidating. But obviously I did all right because I got the job. All right, let's talk about glomerular filtration rate. Let's first define it. GFR is defined as the volume of filtrate formed each minute by the kidney. It's really, that's a true definition. But if we want to maybe put in our own words, we could say that glomerular filtration rate is the rate at which the glomerulus filters. This is true, but it might be simpler to say the rate at which the glomerulus filters per minute. The key thing is there, per minute. Rate at which glomerulus filters per minute. I'm not going to ask you what a normal glomerular filtration rate is. You can see there what it is, but I'm not going to ask you that number. This is a really important thing because this is the first step of urine formation. So how quickly we filter the blood basically sets the tone for the rest of urine formation. So it's really important. Sometimes our body needs to increase how quickly it filters blood. Other times it needs to decrease how quickly it filters blood. And whatever decision it makes to increase or decrease filtration rate will have a domino effect and later impact how quickly or how slowly we produce urine. So in that way, glomerular filtration rate is basically setting the rate for the whole kidney. So even though we're talking only about how quickly we filter blood at the glomerulus, this is really setting the tone for how quickly the whole kidney is going to work. Why is it so important? I mean, do we have to even talk about why it's so important? Because it really sets the tone for the kidneys. And like every other place in the body, we have to be able to adapt. Sometimes we need to filter more. Other times we need to filter less. And because the kidneys also play a role in homeostasis of fluid volume, of blood pressure, of solute concentration, one of the main ways that our kidneys can maintain homeostasis of those things is by altering its glomerular filtration rate. Hopefully I've gotten across to you, even though you can't see me. You can imagine I'm gesticulating and making all sorts of motions with my hands because this is oh so important. All right, so we're going to talk quite a bit about glomerular filtration rate. This slide I don't really want to get too in depth about. All we're going to say is GFR is usually glomerular filtration rate is good. So in other words, the glomerulus is set up to filter at a high rate. Okay, so the glomerulus is set up to filter at a high rate. And that's a good thing. We like that. How is the glomerulus set up to filter at a high rate? Well, we have a high surface area. Think about the glomerulus. It's a ball of capillaries, high surface area. The more surface area we have in the glomerulus, the more we can filter. What else makes the glomerulus set up well to filter blood at a high rate? We have very permeable glomerular membranes. Remember we have those podocytes in between the glomerular capillaries, and they have little extensions, little feet that come off, and in between the feet are filtration slits. The glomerular membrane is very permeable. So things can relatively easily move from the glomerulus into the capsular space. Okay, so the glomerulus is set up well for filtration. High surface area, very permeable membrane, and we have a net filtration pressure in this direction. So all three of these things are helping the glomerulus to be set up very good for filtration. That's fantastic. Oh, wait. Here I built you up, and now I'm going to tear you down again. Even though all the things I just said were true, even though the glomerulus is set up so well to be able to filter at a high rate, it is susceptible to small drops in blood pressure. So we have the good. The good is that the glomerulus is set up well for filtration. But the bad, make a little frowny face here. On the downside, the glomerulus is very susceptible to small drops in blood pressure. That's the bad. So even though the glomerulus is set up well for filtration, it's highly permeable, a lot of surface area, net filtration pressure in the right direction, there is a drawback. The way that it's set up, the glomerulus is very susceptible to small drops in blood pressure. And let's talk about that. We can have a drop in blood pressure of 18 to 20%. And that number may not mean much to you, but if we compare this to other places in the body, other organs, other body systems are better able to handle that much of a drop in blood pressure. Not that it's easy for that's a relatively decent drop in blood pressure, 20%. Not that it's easy for any other organ, but other organ systems are better able to handle that. The kidneys are not. As a matter of fact, if we have as little as an 18% drop in systemic blood pressure, the glomerulus will shut down. It's that serious. And it is for that reason, because the glomerulus is so susceptible to small drops in blood pressure, it is for that reason that this glomerular filtration rate and our ability to regulate the glomerulus in the kidneys is so important. So we can prevent the kidneys from shutting down. So I want to lay out what could happen if we have a 20% drop in blood pressure. You don't have to know all these numbers, especially in the bottom of the screen. I would like you to know that it is at about 20% that a 20% drop in blood pressure can shut down the kidneys. Have an idea about that 20%. Let's walk through this. Under normal circumstances, we have a blood hydrostatic pressure of 60 going in this direction, and we have osmotic pressures of 50 coming in this direction. So if we have 60 pushing out and 50 coming back in, what is the net in this direction? That is what we want. But let's take those same numbers and see what happens when there's a 20% drop in blood pressure. If normally the blood hydrostatic pressure coming in through the afferent arteriole is 60, if we reduce that by 20%, now we have a 48 millimeters of mercury pressure. So now, what if we have 48 as the pressure going out? But we still have the same 50 coming in. So now, what is the net filtration pressure? Now the net filtration pressure is moving in this direction. And actually the numbers down here show you if this goes to 48, then the opposite comes to about, oh no, that's right, never mind. Yeah, 50. So now we have a net filtration pressure coming in because the osmotic pressure, 50, is greater than the hydrostatic pressure of 48. And if our net pressure is this way, we can no longer filter out in this direction. So that's the scenario we're talking about. Not good. So let's talk about regulation of glomerular filtration rate. We're going to talk in a minute about the more specific GFR regulators. But first, I want to make a more global point. If we just think globally, and don't overthink this, please. If glomerular filtration rate is too high, so if GFR is too high, things are moving through the tubules really quickly. And if the filtrate moves too quickly through the tubules, we're not allowing enough time for the tubules to reabsorb good stuff back into the bloodstream. So if it's too high, if we filter too fast, what could happen is we push filtrate through too quickly and we lose a lot of good products in the urine. On the other hand, if our filtration rate is too low, things are moving too slowly through the tubules. And if things move too slowly through the tubules, we could have too much be reabsorbed. And if too much is reabsorbed, we may be reabsorbing waste products that are usually lost in the urine. So just review that globally. Now let's get into the specifics. We're going to talk about intrinsic ways that the glomerular filtration rate can be regulated, and we're going to talk about extrinsic ways that we can regulate the glomerular filtration rate. We're going to start by talking about intrinsic controls. And our intrinsic control is going to be autoregulation. We've heard that word before. We are familiar with it. Here we come across it once again. So, renal autoregulation. This is the ability of the kidneys themselves to autoregulate in response to smaller fluctuations in blood pressure. So it's autoregulation, the kidneys regulating itself, and it's able to maintain the appropriate filtration rate in response to smaller changes in arterial blood pressure. Smaller changes. Okay, we're going to get a little bit fancy. We're going to talk about two specific mechanisms, the myogenic mechanism and the tubuloglomerular feedback mechanism. Before we do that, let me just remind you, just like we talked about with other autoregulation mechanisms, how does an organ autoregulate? Usually by constricting or dilating arterioles. And it's no different here. We're able to constrict or dilate the afferent and even sometimes the efferent, but mostly the afferent arterioles feeding into the glomerulus. All right, let's attack each of these at a time, myogenic and tubuloglomerular. We're talking about autoregulation. I do want to make a point. That before we go on, these are short term. So this is how our glomerulus can regulate itself in the short term. It's a quick fix. All right. You may not like pictures like this, but I think it's the best way to talk about what's happening. So bear with me. Let's talk about the myogenic mechanism. So we start from the top and we see if systemic blood pressure drops. So let's say a normal systemic blood pressure is 120/80. And that means that we get about 60 millimeters of mercury coming into the afferent arteriole, into the glomerulus. But if it drops below that, if our overall blood pressure drops, that means that we're going to get less blood of the glomerulus. And if we get less blood of the glomerulus, filtration rate's going to go down. And that could be a bad thing. So what can the kidneys do to try and fix that? So the first two bullet points are our problem. We have a low systemic blood pressure, which means that we have less blood coming into the glomerulus and too low of a glomerular filtration rate. In order to fix that, the kidneys will dilate the afferent arteriole. So really, everyone, myogenic mechanism is just a fancy way of saying what we probably could figure out already. If, for whatever reason, we have not enough blood coming into the glomerulus, how can we fix that? Dilate the afferent arteriole. If we dilate the afferent arteriole, more blood is going to come into the kidneys, and we can do more glomerular filtration. That is it. Okay? So, make sure you know the scenario. In the myogenic mechanism, this is autoregulation. If we have a drop in overall blood pressure, we will dilate the afferent arterioles. And through doing that, more blood will come into the kidneys. We'll be able to filter more blood. If you memorize it one way, you know the other way. It's a much less common problem to have too much blood going to the kidneys. But if it were to happen, if we had too much blood, we would constrict the afferent arteriole. All right, let's talk about the second means of autoregulation. And that's called the tubuloglomerular feedback mechanism. That's a mouthful. I know in this chapter we have a lot of terms. We talked about the juxtamedullary nephrons. We talked about the Yeah, a bunch of stuff. Now we're talking about the tubuloglomerular feedback mechanism. Okay, so we're going to have the initial same problem. So if we have a drop in systemic blood pressure, that means less blood's coming into the kidneys, and we have a lower glomerular filtration rate. As we said before, if the filtrate moves too slowly through the tubules, so if our filtrate moves too slowly through the tubules, too much is reabsorbed. So we have more time for reabsorption. And if we reabsorb more sodium into the bloodstream, that's what this means, more time for reabsorption of sodium into blood. Because remember, tubular reabsorption is when we reabsorb good things from the tubules back into the blood. So when we have a drop in blood pressure, we have a lower glomerular filtration rate. Things are moving too slowly. We can reabsorb too much into the bloodstream. And if we reabsorb too much into the bloodstream, that results in less sodium in the filtrate. So guess what? Remember those macula densa cells we talked about? I know you tried your best to forget about it, but I'm bringing it back. We talked about the juxtaglomerular apparatus. The juxtaglomerular apparatus was where the distal convoluted tubule wraps around and connects back to the glomerulus, and we have those specialized cells called macula densa. Here's where they come into play. So one job of the macula densa, their most important job, is to sense changes in solute concentration, like sodium. So the macula densa, they're perfectly positioned to sense for changes in solute concentration. In that way, I suppose they're similar to chemoreceptors. And in this scenario, because of what happened, lower blood pressure, too much time for reabsorption of sodium back into the blood, there's less sodium in the filtrate. So these macula densa cells, they notice, wait a minute, there's not enough sodium in the filtrate. So how are we going to fix that? The macula densa are going to inhibit a vasoconstrictor. They're going to inhibit the release of a chemical vasoconstrictor. And by inhibiting what usually vasoconstricts, what is the result? Vasodilate the afferent arterioles. If we vasodilate, we bring in more blood flow, we increase the filtration rate, and we fix the problem of having too little sodium in the filtrate. Whew, it's kind of a lot. And if you compare the two, let me get a different color here. If you compare the two, both ended up doing the same thing. In the myogenic mechanism, we dilate the afferent arterioles to increase filtration rate. And in the tubuloglomerular feedback mechanism, we dilate the arterioles, same thing, to increase filtration rate. But the trigger for what causes that to happen are two different things. And this is an example of how we can have two means of autoregulation that end up doing the same thing, but it just gives us more means of doing it. This way, we're not relying only on one. If we only had the myogenic, then we'd only be sensing for changes in filtration rate based off of pressure. Well, our body doesn't want to rely just on one thing. What if that one thing doesn't work properly? We want to have another way. So not only can we regulate filtration rate by monitoring pressure changes, we can also regulate filtration rate by monitoring solute concentration. So it's like a series of checks and balances, two ways to make sure that we can help to regulate glomerular filtration rate. Remember, if you have questions, you can email me I'm here to help you, but I can only do it if you reach out to me, okay? All right, so under normal body conditions, in other words, if we have relatively minor changes in blood pressure, the autoregulation mechanisms are good enough. So if we have normal changes in blood pressure, when you sit down for a while, then you go to stand up, your blood pressure drops. That's a normal, small change in blood pressure. So our autoregulatory mechanisms, the myogenic and tubuloglomerular feedback mechanism, they're good enough. But what if we have a more severe drop in blood pressure? So when we have a more severe drop in blood pressure, then the autoregulatory mechanisms are not enough. And oftentimes, stress makes possible a more severe drop in blood pressure. So when we're under stress or when we have a more severe drop in blood pressure, we can no longer rely just on the autoregulatory mechanisms. Now we have to rely on some extrinsic controls. I'm going to focus on the second one. So even though we do rely on some of our neural controls, I'm going to focus more on these hormonal controls. Sometimes I have to make choices, otherwise we'd be learning about this for 5 or 6 hours. Not that I would mind that, but I think you might. And we might run out of time. So let's talk about when we have a more severe drop in blood pressure or when our body's under stress. We can no longer rely on the autoregulatory mechanisms alone. We have to rely on our extrinsic controls, which, look at it, I know you're looking ahead and you're excited, is the renin-angiotensin mechanism. Wait, I think I hear you saying something. Yes, you're right. We talked about this already in the blood pressure, in the blood vessel chapter. See, it all comes together. So this is going to be familiar. We might talk about it in a little bit different way sometimes, but the idea is the same. Let me see. Yes. This is going to sound very familiar. Let's outline what's most important for you to know. Okay. We activate the renin-angiotensin mechanism when there's a more significant drop in blood pressure. Remember, if we have a more minor change in blood pressure, we can rely on the autoregulatory mechanisms, and that's enough. But if we have a more severe, I'm going to write it down so there's no excuse for us not to be clear, exclamation point. If we have a more severe drop in blood pressure, the autoregulatory mechanisms are not enough, and this is when we're going to trigger the renin-angiotensin mechanism. This looks very familiar. Maybe you like to look at it in the words on the left part of the screen. Maybe you're more visual and you like to look at the picture. So we're talking about a significant drop in systemic blood pressure. Remember, this is only triggered when there's a drop in blood pressure and a significant drop in blood pressure. So if there is a significant drop in blood pressure, the kidneys will release a hormone called renin. Renin goes through a series of chemical reactions until it forms angiotensin II. So it goes through a series of chemical reactions until we get the all-important angiotensin II. Angiotensin II is what does a lot of things to bring blood pressure back up, because that's the goal. Remember, our initial problem is that we have a severe drop in blood pressure. So we release renin, convert it into angiotensin II, and angiotensin II is going to do a bunch of things to increase blood pressure back to normal. We talked about what angiotensin II can do in the blood vessel chapter, but I didn't talk about everything that angiotensin II can do, because we were talking more about release of aldosterone, ADH, making you thirsty, constricting peripheral blood vessels. That's all true. But if we look specifically at the kidneys, One unique thing about the kidneys is that when we have angiotensin II, it constricts the efferent arterioles. Wait a minute. We know that we have the afferent arteriole coming into the glomerulus, right? And then we also have, it's coming in, we also have the efferent arteriole. That's a really bad picture. Let me try this again. Sometimes you just have to know when it's crap and not be afraid to just go back. Okay, let's do a little bit of red. So we have the glomerulus, beautiful little thing. The glomerulus is surrounded by Bowman's capsule. And then we have the afferent arteriole. I'm going to put it in red. The afferent arteriole is where blood comes in to the glomerulus. Let me change color. Let's do green. And we also have the efferent arteriole. And the efferent arteriole is a way for things to leave the glomerulus, right? E for exit. So, if we constrict the efferent arteriole, so instead of it being nice and wide like that, instead of being nice and wide, now the efferent arteriole is narrower. When we constrict a vessel, what does it do to pressure? If we constrict a vessel, we know that constriction will decrease flow. But what does it do to pressure? When you constrict a vessel, it increases the pressure. This was the example of the garden hose I gave in the blood vessel chapter. If we constrict the end of the garden hose, less water's coming out, but whatever's coming out is at a higher pressure. So in this example, our initial problem is we have a drop in blood pressure. So if we constrict the efferent arteriole, it's going to increase the pressure here. And by increasing the pressure, there's actually more of a force coming back this way. It's almost like an afterload, if you think about the heart chapter. So there's a back pressure coming back into the glomerulus, and what it will do is it will increase the pressure overall in the glomerulus, and it'll increase filtration rate. Wow, how cool is that? So, if we have a drop in blood pressure that's severe, we will activate the renin-angiotensin mechanism. Release renin, convert it into angiotensin II. One thing that angiotensin II does is it constricts the efferent arteriole. If you constrict an arteriole, the pressure goes up. And in this case, because this is the efferent arteriole, that increase in pressure comes to mean back pressure back against the glomerulus. In this case, it's a good thing because our initial problem was not enough pressure in the glomerulus, but now we've increased the pressure in the glomerulus to help fix it. So cool. All right, let's just review what else angiotensin II does, because I know you should know all of them. Let's do orange. All right, so angiotensin II, one thing it does is it constricts the efferent arteriole. Another thing angiotensin II does is it stimulates our thirst center. If we're thirsty, we bring in more fluid, we drink more. If we drink more, it increases our blood volume. If we drink more, it increases our blood volume, which increases our blood pressure. Angiotensin II also stimulates a release of anti-diuretic hormone, which is our water-retaining hormone. This is the same information from the blood vessel chapter. So if our initial problem is low blood pressure, if we release ADH, it tells the kidneys to retain more water. If I retain more water, blood volume goes up, and fluid volume, and blood volume goes up, and blood pressure goes up. And then, last but not least, number 4, angiotensin 2 stimulates release of aldosterone. And aldosterone is our salt-retaining hormone. So it tells the kidneys to retain more salt. If I retain more salt, more water is also going to be retained because water follows salt. If I retain more water, increases fluid volume, which increases blood pressure. So make sure you review all of the activities, all of the actions of angiotensin 2. There's a nice summary here, and sometimes I think I've told you this. Sometimes I find these diagrams to be too overdone, but I actually like this one. You might like it, you might not. For those of you that think it's helpful, I think it's a nice summary. These are the actions that happen when there's a drop in blood pressure. Because at the beginning of this whole conversation, what did we say? The glomerulus is set up really well for filtration, which is good, but it's very susceptible to drops in blood pressure. So any drop in blood pressure is really dangerous to the glomerulus. So we have to have a lot of mechanisms to make sure that a drop in blood pressure doesn't result in a shutdown of the kidneys. We had our 2 means of autoregulation, short-term autoregulation, both resulting in dilating of the afferent arteriole. If we bring in more blood flow, we increase glomerular filtration rate back to normal. We didn't talk about the sympathetic nervous system, which is fine, but we did talk about the renin-angiotensin mechanism. This is the extrinsic long-term solution. Kidneys release renin, eventually converted into angiotensin 2, and it did 4 things, right? Let's see if I can look at this on the picture. It constricted the efferent arteriole, led to a release of aldosterone, led to a release of ADH, antidiuretic hormone, and it makes us thirsty. All of these things function to increase fluid volume, which increase blood pressure back to normal. I also have it in word form here. I do want to go back, before we finish off this chapter, I do want to go back, and this is not going to be on the test, but for those of you who might be interested, let's do Navy, I like that. Have you ever heard of there's a class of medications called ACE inhibitors? Again, this won't be on the test, but sometimes having a clinical application can be helpful. ACE inhibitors are meds used to treat hypertension. Hypertension is high blood pressure, right? And this is where we can understand how these ACE inhibitors work. Because ACE is the enzyme that allows angiotensin 1 to be converted to angiotensin 2. That's what it stands for, angiotensin converting enzyme, ACE. It is the enzyme that allows for the conversion of angiotensin 1 to angiotensin 2. So if someone has high blood pressure, one way we can manipulate that to make blood pressure go down is to inhibit ACE. If we inhibit that angiotensin converting enzyme, we don't form angiotensin 2 because we've just blocked the enzyme that lets that happen. And if we don't form angiotensin 2, then we don't let angiotensin do what it normally does. What is the role of angiotensin 2? Angiotensin 2 helps to increase blood pressure. If I block what usually increases blood pressure, what is the net result? the net result is a decrease in blood pressure. That's really bright. Wow. Anyway, not on the test, but that's how the ACE inhibitors work to help decrease blood pressure. Okay, so I'm going to go back to the very end. We already covered the tubular reabsorption, tubular secretion. We covered water conservation. I did talk about the drugs acting on the kidney. They will not be on the test, but they're here in case you are interested. Going too fast. Whew. We did cover this, okay, and we did talk about the countercurrent, and there are some nice summary things at the end. All right, we have finished covering most of the in-depth material. Yay! There's a couple odds and ends we need to pick up on. You can read here the difference between dilute versus concentrated urine. This will not be on the test. I talked about aldosterone, and I talked about ADH, but I do want to introduce a hormone called atrial natriuretic peptide hormone. So actually, I'd like you to know all three of these. Two of them we've already talked about. So just remember, aldosterone is our salt-retaining hormone. Antidiuretic hormone is our water-retaining hormone. They both act in the kidneys. They tend to act in the loop of Henle. Oh, apparently I can't talk at the same time as I'm writing again. ADH is our water-retaining hormone. Okay. I want to add another one. And I'm going to put in a different color. Let's go with green. Oh, how about purple? I like purple. Atrial natriuretic peptide hormone, ANP. This is actually our salt-releasing hormone. So it tends to be the opposite of aldosterone. We're going to talk about that a little bit more in the endocrine system, but I just want to give you an example because I've given you a bunch of examples of salt retaining, water retaining, things that we use to increase blood pressure. ANP is an example of a hormone that is used to decrease blood pressure. All right. ANP as a hormone is actually secreted by the heart, which is pretty cool. I'm not going to ask you that. But you should know that it works at the kidneys. So all three of these hormones work at the kidneys. Aldosterone and ADH work on the kidneys to increase fluid volume and increase blood pressure. But ANP is an example of a hormone that works on the kidneys to release more salt and thereby lowering fluid volume and lowering blood pressure. You can read about the urinating process or micturition. You don't have to know the specifics of it. I think we've covered enough. You can read about incontinence, but again, will not be on the test. Here are some disorders of the urinary system, won't be on the test. Make sure that you just have an idea about hemodialysis. If the kidneys aren't able to work as they should, then we have a problem because we need to be able to filter the blood and produce urine to get rid of a lot of that waste. So if someone has a chronic kidney disease or some sort of chronic condition, I suppose there's acute scenarios also, but anytime there's a more severe kidney issue and the kidney is not able to filter the blood on its own, that person will go to hemodialysis. They'll have an IV put in, and basically blood is taken out of that person, and presumably because their kidneys have not been working, their own blood has a lot of waste built up in it. So an IV is put into that person, and we route that person's blood into a unit. And what do you notice about this unit? It has tubing that allows for a lot of surface area. And what this dialysis unit does is it does the job of the kidneys externally, right? So you put in basically some good things that you want reabsorb back into the blood. So we remove waste and we add the good things, and then we return that blood. Now that blood has been eliminated of waste, and now it has the good products reabsorbed in it. So the dialysis unit acts like an external kidney. And you may be familiar with this, but if someone goes to hemodialysis, they're going to be hooked up to that machine for a couple of hours because they want to get their whole blood volume through that dialysis unit to make sure that it can be filtered and have the good stuff added back in. Pardon me again, I'm so sorry. Okay. You can read about kidney stones, but I won't ask you about them on the test. There's a nice picture of an X-ray with the kidney stone stuck in the renal pelvis. That looks very painful. There's a bunch of information here about measuring kidney function. You do not have to know any of this for the exam. If you're interested, if you work with kidney patients, I'm sure you're familiar with this. It is possible to estimate that glomerular filtration rate based off of how much creatinine is in the serum. I put some information here about acute kidney injury and chronic kidney disease. This will not be on the test. Again, not be on the test. This is interesting because chronic kidney disease is a real problem, and we tend to assess the stage of kidney dysfunction by their glomerular filtration rate, and then their levels of that blood protein in the urine, albumin. You don't need to know these. It's just there for extra. The last part of this lecture goes through some of the material about urine. If I have you for lab, I don't have everyone in this lecture for lab, but if I have you for lab, there's information. I'm asking you to watch a couple videos and do kind of a quote-unquote fake urinalysis. So based off of the results of the urinalysis, to tell me what you think could be wrong with that person. So this information could be helpful. I'm going to cover the basics here. You should be reviewing some of these basics for lecture as well as lab. Urine normally should be pale to clear in color, pale yellow to clear. The specific gravity is a measure of density. You want this to be within a certain range. If we have a high specific gravity, the urine is too dense, and that can often indicate dehydration. The pH varies. You don't have to know this range, but unlike other things in the body, if you think about the blood pH, boy, do we have a strict range. We've got to keep that blood pH in 7.35, 7.45, and that's it. The urine, we're much more lax. So you could have a healthy urine pH of 4.5. You could have a healthy urine pH of 8. Either way. And the reason that's okay is because we're using urine as a way to get rid of things, and it's going to the outside of the body. So we actually don't mind if it's acidic or a little basic because we're getting rid of bad stuff. And you should review the chemical composition. Healthy urine should be about 95% water and only 5% solute. Of the solutes, the highest amount of solute you'll have is urea, which is a end product of protein breakdown. We talked about in the last chapter on metabolism that proteins are kind of a pain in the butt because they have that nitrogen on them, and we've got to strip off that nitrogen, and in the process we often form urea, or we can form ammonia. Anyway, you should know that the highest amount of solute is urea, which is a protein breakdown product. The rest is all extra. I would like you to review the normal urine output. So a normal urine output per day is about 1 to 2 liters. Of course, we're all different, but that's a roundabout reasonable estimation. And then these can be helpful as you go through the lab. I'm not going to ask you any of these in the lecture exam, but these could help you in the lab as you're trying to answer the questions. Okay, we're going to end there. This is a good chapter, but it does require some study. If you have questions, I am here. All right, see you next time.